Well, to continue right where we last left off, we know how to find the period for a mass spring system. It's 2 pi times the square root of m over k. And that just means a really heavy object vibrating when attached to a spring is going to take more time because it has greater inertia. And so it's no surprise that mass is found in the numerator of this equation. If the spring is stiffer, it pulls more forcefully and the object vibrates faster. Therefore, as the spring stiffness increases, the period decreases. Now we also know period for a physical pendulum. It's equal to 2 pi also times the square root of, in this case, it's the square root of the moment of inertia divided by the product of weight and lever arm. So for example, we can find the period of a physical pendulum made out of a uniform rod that's hinged not at its end point and certainly not at its center. If you hinge it at its very center, it doesn't swing at all. So let's imagine the case where it's hinged halfway between the value of R is equal to L over 4. So period would be equal to 2 pi times the square root of, now the rotational inertia, if it were hinged through its center instead of through this axis, the rotational inertia, hopefully you remember for a uniform rod, is 1/12 ml squared when rotated through its center, so we'll call that I naught. So the rotational inertia about the axis we've chosen can be found using the parallel axis theorem, so it's equal to I naught plus md squared, and in this case the distance is 1/4 the length of the rod, so I would be equal to 1/12 ml squared plus m times 1/4 L quantity squared, which would give us 1/16 L squared. So the question is, what's 1/12 plus 1/16? We need to find a common denominator for that one. So how about 48, right? You can say I is equal to 4/48 ml squared plus 3/48 ml squared, which gives us 7/48 ml squared. All right. Then we have to divide this by mgr, so divide by mg, and r is L over 4. Okay, so m cancels out, one of the L's cancels out, and 48 divided by 4 is 12, so we get t equals 2 pi times the square root of 7/12 L over g. If we were together in a classroom, that would be an interesting experiment, wouldn't it? If we could find a uniform rod and measure its length using a meter stick, this is very easy data to collect. And then all we'd have to do is pass a bolt or something that could act as an axis of rotation through a hole that's located at 1/4 the length of the rod, and then let it swing. And instead of letting it just swing for one vibration and time that, it would probably make sense to let it swing 10 times. Go there and back, 1, there and back, 2, there and back, 3, and so on. And then if we could time 10 swings and divide that by 10, then that would be the period. And so we could collect this just by observation, but then we could apply this formula and see if the directly measured value for the period matches the theoretical value based on this calculation. So we'll save that for another date. How about this? Do a simpler version of the pendulum. Instead of a rod, what if we just took a point mass and hung it from a string? So this is what we mean by the simple pendulum as opposed to the physical pendulum. So we've got a mass of m sitting at a distance of r, where r is nothing more than the length of the string from some hinge at the top. We pull it back some initial angle theta max, and we apply Newton's law for rotation of force of gravity, mg, pulls. We could extend this lever arm along this line of action, so this angle theta is the same as this one. So there's a net torque equal to r cross mg. That means I alpha is equal to negative mgr sine theta. I times the second derivative of angular position with respect to time is negative mgr sine of theta. Let's see. The second derivative of the angle with respect to time is negative mgr over I. Now, in this case, I'm going to use the Maclaurin expansion, or the infinite series replacement for sine theta, which says sine theta is theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial plus minus theta to the 7th over 7 factorial, and so on. Now, if theta is a relatively large angle, remember on the unit circle, where does 1 radian sit? 1 radian is more than 45 degrees. 1 radian is about 57 degrees. So we can approximate sine of 1 radian as 1 minus 1 over 3 factorial. So 3 factorial is 3 times 2 times 1, so 1 minus 1/6 plus 1, see, because 1 cubed is still 1, and 1 to the 5th is still 1. Okay, and then 5 factorial, 5 times 4 times 3 times 2 times 1. So 5 factorial is 20 times 3 factorial, which is 120, and on and on and on. Okay, so we end up with a value that's, I'm not going to apply the whole expansion, but if we use our calculators and just take the sine of 1 radian, we get 0.84. But let's try smaller angles. Instead of 1, let's try something like 0.2, right? 0.2 radians that's about 11.5 degrees or so. Okay, so sine of 0.2 radians, according to this Maclaurin expansion, is equal to 0.2 minus 0.2 cubed over 6 plus 0.2 to the 5th power over 120 minus, you can see, without even plugging in your calculator, you know this is going to be a very small number, right? In fact, the smaller theta becomes, the less significant these higher order terms in the expansion, and so as long as theta is small, the expansion for sine theta can just be replaced with the first term of the expansion. That's pretty mathy. So in step 5, we can say approximately the second derivative of position with respect to time is approximately equal to negative mgr over I times theta. So everything we're deriving for the pendulum is an approximation based on small angle. If you swing your pendulum from extreme angles, if you attach a bowling ball to a rope and you let it hang straight down and you pull it back 5 degrees, 10 degrees, even 20 degrees and let it swing, you can have a pretty good prediction of what that period of vibration is going to be. However, if you choose to pull that back at an angle greater than 50, 60, 70 degrees or so, then you can't really effectively get a great prediction based on the math we're going to do here. So you know the drill from here. We got to make a guess. I'm going to guess what type of function for theta as an expression of a function of time can I take the second derivative of so that I get negative some constant times that very function I'm guessing. And you know exactly how this goes. We've already done it before. We're going to guess that theta is equal to theta maximum, which is just the angular amplitude multiplied by cosine of some omega t. By the time we take the second derivative of this expression, we get negative omega squared theta max cosine omega t, but all of that is just theta, so everything is fine and good as long as omega squared is mgr over I. So omega must be the square root of mgr over I, which means frequency must be 1 over 2 pi times the square root of mgr over I, which means period must be 2 pi times the square root of I over mgr. Now, why am I repeating myself? That's just the same thing we had started out with back here. Right. Well, all I'm suggesting is that the simple pendulum is a special case of the physical pendulum, but it's a special case for which we know without a doubt what the value of I and what the value of R is. For the simple pendulum, R is the length of the rope or the string, and I is I of a point mass, which is mr squared, or ml squared in this case. So the period for a simple pendulum is 2 pi times the square root of ml squared over mgl. The m cancels out, one of the l's cancels out, and we have period equals 2 pi times the square root of L over G. And notice that it's independent not only of amplitude, as is true for all simple harmonic motion. You may recall that for a mass on a spring, it doesn't matter how far you pull it back, that's not going to change the period of vibration. It's only the mass and the spring stiffness that affect it. Well, in the case of the pendulum, the mass doesn't even affect it. The period of a pendulum is independent of amplitude and independent of mass and only depends on the length of the pendulum. That means you can take a long string and hang hang your keys from it, right? Or you can take that same string and hang a bowling ball from it. They should have the same period. Now, roughly speaking, you might have to make the string a little bit shorter in this case to account for the radius of the bowling ball. The length of the pendulum is not the length of the rope. The length of the pendulum is from the top of the rope to the center of mass of the pendulum bob. Okay? A grandfather clock keeps time with the use of a pendulum. So there's a rod with a mass on the end of it, and it swings back and forth like a simple pendulum. And I think as it swings over this way, you can hear it go tick. And there's some ratcheting mechanism that gets moved forward and advances 1 second to make the second hand on the clock move around. And then on the return swing, it goes tock. And so the period isn't 1 second, the period is actually 2 seconds, right? 1 second there and 1 second on the way back. So what's the length of the pendulum in a grandfather clock? If we rearrange this equation, period squared is 4 pi squared times L over G. So L is GT squared divided by 4 pi squared. Something really interesting here. This is just a coinky-dink about our Earth at sea level. I don't know if you ever tried this before, but try it right now on your calculator. What's pi squared? Isn't that interesting? Pi squared isn't that far off from 9.8. So we could just say that L is equal to t squared over 4, as long as we're willing to accept that the units cancel. Obviously that can't be quite right, because period squared would be units of seconds squared and length would be in units of meters, but as long as we're assuming we're going to work in the MKS system, the length in meters is the period in seconds squared divided by 4. oh my goodness. And if the period of a grandfather clock is 2 seconds, lo and behold, the length of a grandfather clock is darn near 1 meter. Now, if we actually plug it in and keep more sig figs, I think the length of the pendulum in a grandfather clock is like 0.99 meters or 99 centimeters. So that's interesting. Wall clocks behave in the same way, or like a cuckoo clock, right? They're just a lot shorter, but they also have a pendulum in there that swings back and forth. And I believe with the cuckoo clock, when it swings there, you don't hear any tick. It's only when it swings back that you hear it. So the way the ratcheting mechanism works is that the period is 1 second, not 2 seconds. It doesn't advance the movement of the second hand on the way there. It only advances on the return part of the swing. So if this is right, if period squared is equal to 4 pi squared L over G, then L is equal to gt squared over 4 pi squared. The pi squared and the g cancel out, and so if we do 1 squared divided by 4, we get very nearly 0.25 meters. So the length of the cuckoo clock isn't half the length of a grandfather clock, it's a quarter the length. Well, yeah, that's because there's a square root in the equation, right? It's not a direct relationship between t and L. Period is proportional to the square root of length. So, yeah, the length of a wall clock is about 25 centimeters, and the length of a grandfather clock is about 99 centimeters. Now, if you move to a higher altitude, if you go from sea level up to the mountains and you take your grandfather clock with you, then G at higher elevations goes down. So to keep the same amount of time, what has to happen to the length? That would also then have to go down. And so the pendulum in these grandfather clocks has this weight on it that you can slide up or slide down in case your clock isn't keeping correct time.